Are we ready to rock and roll tonight or what? Tonight our topic is solving linear quadratic system of equations, and tonight we're going to focus on the method of doing it algebraically, and then in the next video we'll focus on the method of doing it graphically as opposed to algebraically. We've seen a lot of linear systems. We've seen two linear equations or a system of 3 by 3s, but tonight we're going to introduce quadratics. And we're really going to grab your hard hat because we're going to have to go to work tonight and really do some serious algebra. Now, I think the easiest way to introduce this topic is to consider it graphically first and foremost. And so imagine that I've got a quadratic function here and I graphed simultaneously a linear function. And the solutions are these intersection points right here. So in this particular graph, there would be considered two solutions. Negative 3 comma 0 would be the first solution, and the ordered pair 5 comma 8 would be the second solution. In other words, that's when it's a solution, it satisfies both the blue quadratic function and the red linear function. Tonight we're also going to lump circles into the story and consider them a quadratic just because the x is being squared. And again, we'd have, you notice visually the two intersection points. So right here at 4 comma negative 3, that's a solution. And here at negative 4 comma 3, that would be the second solution. So let's introduce you to our first system of equations tonight. And what we have here is a linear function, and one of the easy ways to tell it's linear is neither the x nor the y is being squared. We've got an invisible 1 for both exponent. And then the second function here is a quadratic, and you notice the x is getting squared. Okay, so what is our goal tonight? Our goal is to find every ordered pair that what? And here's a special word, satisfies, okay, both equations. And we're going to talk a little bit about what it means to satisfy an equation here. So our question here is, does 4 negative 1, is it a solution? In other words, does it satisfy both the linear and the quadratic function? So what I'm going to do is I'm going to do a simple substitution and just remind myself that here's my x and here's my y coordinate. So I'm going to start with the 2x equals 3y plus 11, and I'm going to substitute the 4 for x and the negative 1 for y. And let's see, we got 8 equals negative 3 plus 11. And sure enough, negative 3 plus 11 is equal to 8. So boom. Now we're halfway home, and that means we should go check the second equation here. Slide this bear up a little bit. So the second equation was y equals x squared minus 3x minus 5. And I'm going to go ahead and substitute negative 1 for y and substitute my 4 for the x. And let's see, negative 1 equals 16 minus 12 minus 5. And feel free to use the calculator, but indeed negative 1 equals negative 1. So yes, we would declare that 4 negative 1 is a solution because it satisfied not just one of them, but both of them simultaneously. Now on the other side, again, let's test that same process. Is negative 5 comma 2 a solution? So we'll start with the linear function. Whoops, that should be an equal sign right there. 3y plus 11. So let's say 2 times negative 5 equals 3 times 2 plus 11. Negative 10 equals 6 plus 11. Or in other words, does negative 10 equal 17? And I'm going to say no. And right there, as soon as it doesn't satisfy the linear, don't even waste your time checking the linear. We'd say that negative 5 comma 2 is not a solution. So I think we're going to just dive in with both feet into our first example, and then after we get through this example and we survive, we'll kind of reflect on it, pick up some pieces, and we'll kind of generalize some of our steps and write them out in our notebook. But the name of the game tonight is a method called substitution. The last couple of nights, you've talked a lot about this elimination method, and tonight we're going to rely on substitution. So here's the trick. Start with your linear function and see if you can solve for y. And I would subtract 5 from both sides. And in other words, what we're in right now is what we call slope-intercept form. And you know that this y coordinate is equal to 3x minus 5. So what I'm going to do is I'm going to take this quantity right here and I'm going to substitute it for the y in the other equation. In other words, the nonlinear equation. And so now that nonlinear equation looks like x squared plus the quantity 3x minus 5 squared equals 25. Because this y right here became a 3x minus 5. And let's see, and I'm going to take my sweet old time here and just repeat the 3x minus 5 so I can kind of set myself up to FOIL it all out. And I got x squared plus, let's see, I'm going to do a little distributing. So we got 9x squared minus 15x, and then I'll do a little more distributing. Minus 15x plus 25 equals 25. Now, here's the key, and here's what's real special. I'll put a star right here. I've got a beautiful equation that's in terms of just one variable. And I'm just going to combine all my like terms. So if I combine my x squareds, I get 10x squared. If I combine my x's, I get negative 30x. And if I subtract this 25 from both sides, ironically, they cancel out, so it just becomes 0. And I'm going to solve this equation just like I would any other equation. And this looks like the GCF is my best approach, so I'm going to divide both terms by 10x, thus leaving me with the quantity x minus 3. By the time I tee this up and use the zero product law, if I set each of the factors equal to 0, I'm getting x equals 0 because I divided both sides by 10, and x equals 3. Now the key here tonight is we're not done yet. We're looking for ordered pairs, remember? And so what I'm going to do is I'm going to take this x value and I'm going to substitute it back into the linear function. And if you recall, that linear function was y equals 3x minus 5. And so if I substitute the 0 for x, I get y equals negative 5. And I'll do the same thing with my other x value. So it's going to be 3 times 3 minus 5, or 9 minus 5 is 4. So when I'm all done, I'm going to express my answer as a couple of ordered pairs. The first one was an x value of 0 and a y value of negative 5. And the second solution had an x value of 3 and a corresponding y value of 4. Okay, now if that one was a wild blur, don't panic. We're going to do a few more examples, and we're going to kind of try to generalize each of these steps now that you've seen one worked out. Okay, this is probably going to be your least favorite slide of the night, just because we're going to write down some really important things, and it's going to take you a little time, and certainly feel free to use your pause button so that you get every detail down, and it's certainly going to pay off. There's no doubt about it when it comes time to work on your homework in class tomorrow and review for the test later in the week. But the key is we're going to identify which of the equations is linear, and we're going to solve that linear equation for y. And our lingo is that when we solve it for y, we say the equation's in terms of x now. And now, ironically, there may be times where I twist that around and say, okay, we're going to solve the equation for x so that's in terms of y, just because it's easier to do. But I'll point a couple of those out later. This is equivalent to rewriting the equation in what we call slope-intercept form. What do I mean by slope-intercept form? Well, that's like y equals mx plus b. Technically, we could work with the quadratic equation first, but it's usually more difficult. So that's why we tend to favor the linear equation. Okay. Now, here comes maybe the most important step of the day today. And again, you're just thinking substitution here. We're going to replace the y in the quadratic equation with the expression involving x from the slope-intercept form of the linear equation. Now, that might sound pretty complicated, but we'll repeat it a few times in the next couple of examples, and you'll see exactly what we mean by replacing the y in the quadratic equation with the expression involving x from the slope-intercept form. This will yield an equation in one variable. Okay? We want to work our way from two variables to just one variable. All right, what's next? Okay, it gets easier now. We're going to solve the quadratic equation for x. Easy enough. And then we're going to substitute that x back into the linear equation to find the corresponding value of who? I bet you can fill that one in. Yeah, we're looking for the corresponding value of y. Now, on the example I just did, the numbers were super nice and easy, and I didn't use my calculator. But as soon as the numbers get a little ugly, we're going to store those solutions that you just got for x in your calculator, and we're going to use that store feature to check your answers. Okay, just to make sure they satisfy both equations. And then last but not least, don't forget this. We're going to express your final solution as an organized, ordered pair. Okay, make it really obvious when you're all done what your final answer is. Okay, and that's just a good quality of a great math student. Okay, for our next example, I'm going to try to follow the steps that we just wrote in our notebook step by step, and I'll try to point out what each of them is trying to tell us. And we're going to identify the linear function first, and that's this one right here. So identify my linear, and I'm going to try to solve this for y. In other words, I'm going to subtract 11x from both sides. And this is now what we call slope-intercept form. And I'm going to take this expression, negative 11x minus 35, and I'm going to substitute it into the quadratic equation over here. And that's going to give me negative 11x minus 35 equals x squared plus x. Now I think we're in the clear. We're just going to solve this quadratic like we would. And we always want to move all the terms to one side. So I'm adding 11x to both sides, thus giving me 12x. And I'm also going to add 35 to both sides. I don't think I have to worry about a GCF. We are working with a trinomial, so I'm thinking multiply, add, multiply. Multiples of x squared are simply x times x. And the multiples of 35 are going to be, in this case, positive 7 and positive 5. We'll tee those rascals up. X plus 7 equals 0, therefore x equals negative 7. And x plus 5 equals 0, therefore x equals negative 5. Now we're not quite done. Let's see. We're going to substitute these back into the linear equation. And I'm just going to, we go negative 11 times negative 7 minus 35. Let's see, y equals 77 minus 35, so y equals, let's see, 42. Boy, that's a big bear right there. Or we could say y equals negative 11 times negative 5 minus 35 there. Y equals 55 minus 35, so y equals 20. Make sure it's a minus sign. So when I'm all done, I just want to express my solutions as ordered pairs. So I'm thinking negative 7 comma 42 is my first solution, and negative 5 comma 20 is my second solution. And the checking will take place on my calculator, and it would be one at a time. It would be a matter of substituting these values into the linear and the quadratic, and then pausing and substituting these values into the linear and the quadratic. Our next example here is kind of gives me a bad feeling right off the bat because they said round our answers to the nearest tenth. So that kind of gave me the impression that this one's not going to end up factoring as nicely, and I'm already have this feeling that I'm going to end up using the quadratic formula at some point to solve the quadratic equation. But anyway, let's identify the linear function. And what we're going to do is we're going to try to solve for y. And in order to do that, I'm going to add 7 to both sides. Okay, now we're in what's called slope-intercept form. I'm going to take the expression, or the quantity 3x plus 7, and substitute it into y in that quadratic equation. And once I make that substitution on the left side, we're going to try to set this quadratic equation equal to 0. And in order to do that, I'm going to subtract the 3x from both sides. To give me minus 7x, and I'll also subtract 7 from both sides to give me minus 6. And again, we could sit here and try to do guess and check and factor it, but I don't think it's factorable. So let's make a little note here. If it's not factorable, okay, that's an indication that we're going to use the quadratic formula, okay? X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So here's what I'm looking like. I've got negative 6 plus or minus 6 squared minus 4 times 6 times negative 6 divided by 2 times 6. Okay, and I'm using my calculator. I got it right next to me here. And my discriminant, or in other words, the 36 minus 4 times 6 times negative 6, turned out to be 193. Now here's a little shortcut that I'll share with you, is that especially if I'm going to eventually express my answer in terms of a decimal, there really is no sense in trying to simplify that radical. So I'm just, on my calculator, I'm using alpha F1 and to get that fraction set up. And I'm going negative 6 plus the square root of 193 divided by 12. And I got an x value of 1 point. Check this out. I'm going to write them all down. 7, 4, 1, 0, 3, 6, 9, 9, 9. And of course the decimals continue to go on even though I can't see them on my screen. And I'm going to store that bear as alpha A. And then I also I went back to alpha F1. I did -6 minus the square root of 193. And please verify this on your calculator to make sure that I'm not screwing this up. Sometimes I goof it up myself. Negative 0.57437.03325. Decimals continue, and I'm going to store that in alpha B. All right. Now remember, we're not quite done because all I've got is the x values, and now I need to find their corresponding y values. And so going back to alpha A here, I'm going back to the linear equation, which was 3x plus 7. And I'm going to type in 3 times alpha A plus 7, and that gave me 12.223111. All right, on the other side, I'm thinking 3 times alpha B plus 7, and that's going to give me 5.27688. Let's see, 9, yada, yada, yada. Okay. And so now I just need to express my answers, and I think they want me to round to the nearest tenth. So my first solution would be 1.7 and 12.2. And my second solution would be -0.6 and 5.3 rounded to the nearest tenth. We'll pull those squigglies around. That's kind of like my way of announcing that's my final answer. Well, I saved the best one for last tonight, and the good news is I don't think this last one's as ugly as the previous one. And I want to show you a couple of tricks. So here's your, whoops, don't move there. Let's see, I grabbed the wrong, here we go. Here's your linear equation, right? And in our notebooks, our first step, we said we're going to identify which one's linear and then solve it for y so it's in slope-intercept form. Well, here's an insider's tip. If the x is already by itself, then you're actually okay. What we're going to do is we're going to take this expression y plus 7 and we're going to substitute it for the x values that we have here. Now, you know, that's not to say that you couldn't have solved this for y and substituted for the y's instead of the x's, but I just think that's wasted effort that you don't need to invest into this question. So let's rewrite the quadratic, and in fact this is a circular equation just because you've got both the x's being squared, both the y's being squared, so we're working on a linear in a circle. And let's see, that first term, instead of being x squared, is now going to be the quantity y plus 7 squared. The second term is still y squared. The third term is going to be minus 12 times the quantity y plus 7. The fourth term stays minus 4y. Fifth term is still 31, and we're still equal to 0. Alright, we're going to take my sweet old time here and just repeat the y plus 7. And as I FOIL it, I've got y squared plus 7y plus 7y gave me 14y plus 49. And then the next term was a y squared. I'm going to distribute my negative 12. That's minus 84, I hope. Minus 4y plus 31. Wow, what a wild equation we have here. But it's really not that bad. We're going to just focus on combining like terms right now. And for instance, if I combine y squared plus y squared, that gives me 2y squared. If I combine 14y with negative 12y, that gives me 2y. And if I subtract 4y from that, I've got negative 2y. And then last but not least, I want to combine my 49 with my negative 84 with my positive 31. And I think that gave me negative 4, and we're equal to 0. Now I could actually simplify this equation by pulling out a GCF of 2. And luckily, I was holding my breath a little bit, but I think this one is factorable. I think I could go minus 2 plus 1. We'll tee this bear up. Now, this is just a matter of formality right here, but the first factor was 2, and we're setting that equal to 0, which, you know, that's a dud. 2 obviously doesn't equal 0, so there's no solution there. But y equals negative 1 is a solution, and y equals 2 is a solution. And what I'm going to do is I'm going to substitute those both back into the linear function so that I can solve for x. Now remember, x was equal to the quantity y plus 7, so x is equal to negative 1 plus 7, so therefore x equals 6. Or we could say x equals 2 plus 7, therefore x equals 9. and my ordered pairs, the first one's going to be 6 comma negative 1. Now they almost tricked me right there. Make sure that you do express your x value first and your y value second. And then the next pair would be 9 comma 2. And bada bing bada boom, there's our two solutions, and we could easily type them in by hand or using the store features on the calculator to verify and check those solutions. So hope you enjoyed the algebraic method. Tomorrow we're going to solve similar questions but using a graphical method to find our solutions. Have a great night. We'll catch you tomorrow.